introduce a great scientist, humanitarian, a friend of mine for many years, M.Kapranov, who is going to tell us something about doubly perverse sheaf or indifferently perverse schobers.
Okay, thank you so much. And I apologize for not submitting my title in time. It's too late, so the title will be Perverse schobers surfaces. Fukaya categories with coefficients. And the algebra of the infrared. So this is some overlapping projects with Tobias Dickerhoff. Vadim Shachman and Jan Sokolov. So I would like to start by discussing ordinary perverse sheaves and their relation to skeleton, as appeared in this conference already. So let me call this part. Perverse sheaves. So it is also a little like Maxime's marriage made in heaven. So there is somehow perverse sheaves that do like or love skeleton. They love skeleton, really. And perverse sheaves like love skeleton more than non-perverse sheaves.
The real perverse.
The real perverse, yes.
Real perversity in heaven
Yes,
like
yes.
skeleton.
That we should call them mortgage.
Huh? Okay, yeah. Okay, they do love skeleton. Let me explain why. So we have, so first let me just fix the notation. I want to explain what is a perverse sheaf. I just write that there is a category of perverse sheaves corresponding to a stratified space. So X is a complex manifold. It's n-dimensional. So it is a stratification. So something, every stratum is smooth, but closures of the strata may be singular, something like this. So, but X is also smooth. So it's an abelian category, which contains the category of local systems.
So if it's a complex manifold with complex stratification, if it's a symplectic manifold with symplectic stratification.
That's probably possible, yes, yes. So in general, so the good perversity is to have stratification by even dimensions. But most of the intuition comes from the complex case. So we can assume, so for now let me assume that it's complex or maybe even Keller, just to relate it with the symplectic picture. So it's therefore symplectic. But we can assume that probably it's symplectic right away. So there is a class, so can speak about singular Lagrangians which are, I'll roughly call skeleton. Call them K and side Ks. So really the reason why perverse sheaves are better in this respect is that often when the skeleton, maybe I could make some rough picture, but the picture is not very, but I can draw something like this. So what really happens is the purity phenomena. Oh, let me write often. It often mean when K, this is sort of well behaved with respect to the stratification. So we have purity. For a perverse sheaf here, the perverse sheaf is a complex. I normalize the shift of the complexes such that local system in degree 0 is perverse. It's a matter of convention. And the purity means this, that we can consider sheaves of hypercohomology with support in K of this F. And that they vanish for I not equal to n. So, and if they all vanish for I not equal to n, then the remaining one, let's call it H n, K of n. So it's a sheaf on K. So let's call it R K of n. So then we have a function from this to this, from the category of perverse sheaves to the category of ordinary sheaves on K. And this is an exact functor of abelian factor.
What does it mean, well behaved?
Well, this I'll give some examples, but in general it's a microlocal property, so it should sort of hit it in the correct way. So I'll give an example in 2 dimensions. There are examples in higher dimensions. A good example would be, suppose you have a complex space Cm, and consider stratification given by something, by strata, which are given by real equations, say hyperplanes with real equations. Then on Rn, and take Rn as a scalar, then it will be true. A good example, which is not completely obvious. So it hits sort of everything in a good way.
Does it mean that strata of this skeleton are Lagrangian in the strata of S?
Yes, in particular, yes.
I have some another definition. What is exact functor? I know the definition.
Exact functor, so that's abelian category. So short
abelian
exact
category
sequences.
is something very complicated about stability, T structures. What is terms of infinity categories exact functor means? Do you have any idea?
Infinity
Because
means nothing. It means nothing because it is just an infinity structure, as Carlos was discussing yesterday, gives you exact triangles.
But exact functor, what for people
Exact functor means the short exact sequences go to short exact. It's an abelian category, and short exact sequences of perverse sheaves go to short exact sequences of ordinary sheaves.
Yeah, it's still.
It's written.
It's what is it here?
No, a priori it would be a long exact sequence. If there are many of them, it would be long exact sequence. It means that somehow if we describe,
But if you have 2 categories with T structures, what does it mean?
it means that the positive part goes to positive part, negative part goes to
Okay.
Okay, yes.
Okay, yeah. That's the I wanted to know. Yeah. Okay.
exact functor of abelian categories.
But did you know a general characterization of what K is well behaved with respect to S?
No, I don't know a general state. No, but I think it should. The condition should be that approximated by something when real part of the holomorphic function greater than 0. So that's what happens in all examples. So, or in this case, if I take space of global sections of this unique sheaf, this simply nth cohomology with support of xn. So, and a good example when this is true is the case of a Riemann surface. X is a complex curve or topological surface. So the stratification S is just a bunch of points. So allowed singular points. Then purity true for any graph. Purity holds for any graph.
With vertices.
No, it might not have vertices. It was even better.
What is the meaning of those 2 cohomologies?
What?
Subscript K and
Cohomology with support. So maybe I should say that, like Maxime was talking about Fukaya category with support. How we can think very roughly of the Fukaya category. This is a complete approximation. Well, it's something like categorification of cohomology. So we have in topology, we have cohomology with support. So we have sheaves. So the global cohomology with support, this is sheaf of hypercohomology with support. So it's just part of the standard format.
But you got SJ.
Not yes, it's an SJS for sure, yes. Yes.
Sorry, I don't understand this curve example.
Huh?
I don't understand this example of the curve. I mean, if I take just the local system, you're
Yes.
saying,
Yes, I'll explain in a moment. I'm exactly going to continue this. Yes, I haven't finished. So let me just formulate a statement and then explain it.
So any graph is well behaved according to
Yes,
the definition?
yes.
Even though vertices, if they're outside of the points, they are not Lagrangian at the corresponding strata.
Yes.
It's not necessary. Yeah?
It's not exactly necessary because we may think that that point is also a strata, except nothing happens in that strata.
Ah,
Okay? So let me formulate a statement. Let me expand on
Before
it.
you formulate the statement, can you move the middle border?
Middle border up or down?
Yes, up, more.
Like this?
More.
And this?
Yes, that's fine.
Ah, because not to make shade on the.
Yeah, the shadow. No.
Not to make shade.
Then move it now.
Not to what?
There is a shadow
put
from
a
the
shadow
middle
in
board to the bottom board.
Oh, okay,
yeah,
okay.
right, yeah, sure.
Understood. Yes. The shadow, okay. A proposition. So let F be any constructible complex with respect to the stratification. Means that it's a complex of sheaves with cohomology being locally constant outside those points. Yes? Then the following are equivalent. First, F is perverse. Second,
So N is stratification for you.
N is a bunch of allowed points.
Allowed points.
So you have something like
It's in this example of surfaces.
yes. Of the surfaces, yes.
and X is smooth, yeah?
X is smooth, yes.
Riemann curve.
Yes. So for surfaces, yeah. For topological surface. The first, and number two, for every graph K inside X, they have only one hypercohomology. So the cohomology with degrees not equal to 1 is 0. Yes, so now let me get to Mohammed's question. So suppose F is a constant sheaf. That's it, we have a graph. Then we have only H1. So only H1 is support with K of sequence. And the stock of this thing, if we write the longer exact sequence, the stock of this at a D plus 1 variant vertex, so stock D plus 1 variant vertex is isomorphic to, say, C to the D. And this is sort of decategorification of the original Maxime's picture with the A D equivalent. So maybe I should say again that in general, so in general, huh? Yes. I can even drop that. Yeah. Yeah. No, if a sheaf is such, if a constructible sheaf, no, the statement is you have a constructible sheaf, which is constructible with respect to a bunch of points. No, suppose.
It's already constructible.
Yes. Suppose it's such that there is only one thing here, then it is perverse. So it will not be true if it is just a single constructible sheaf, not perverse. For appropriate graph, it will be not pure. So in general, dim x equals to n. So then we have the sheaf Hn is supposed to k of Cx. So this is decategorification of the Fukaya category. Of X. And for good types of skeleta, such as, for instance, the Nadler-Zark-Barreal singularities, there is only one HN. So, again, for K only.
So it will be something like K0 this for local.
Yes. So yeah, it would be the K0 would be this. Yeah. So if you just look, we see that what we are doing, we are categorifying cohomology with support, and sheaves of cohomology with support. So there is only one such thing. Then just working with this sheaf gives us the full result. If there is more, then it's kind of awkward to deal with categories in this set. Let me just continue. So more about surfaces. So suppose K. So assume. What should I say? Suppose X allow to have boundary and corners. So corners simply means that we mark some points on the boundary. It's just a way of not keeping this thing as a part of the notation. Suppose this is X. Then we can speak about spanning graphs for such data. For X n. So I depict n by such bunch of start points. It means, so first of all, that legs end in corners in a one-to-one way. Something like this, something like this, something like this. It means also that K contains all the points. So now it's important for me that it contains all the points. And 3, that X retracts to K. Well, relative to F. So that's a standard concept of a spanning graph for a surface with holes. So there should be at least one hole so that we can talk about this. So in this case, K is for F, we can write that H0 of K at K of F, which is the same as this H1, which is the same as H1 K of XF, is simply identified with cohomology H1 of X modulo pure boundary of X with coefficient. So this is pure boundary, which means dx minus corners. So in this case, we again have the phenomenon that we define something in terms of the graph, but the corresponding thing has transparent topological meaning as cohomology, global cohomology with appropriate condition of the surface. So it's better to do like this so that there is no shadow. Okay, so now let me discuss an example of schobers on a disk. Again, sort of into parts. On the disk part, I write phenomena with perverse sheaves, and here I write the categorification. For existence of this, yes. Yeah. This is sort of a version of the Liouville domain.
For existence of this, what is this?
Huh? The condition that you need a boundary for the surface. So in order for this to be applicable, to be able to say this, the spanning graph should exist. So I recall, so this has been discussed so many times already. So suppose I have a disk, there is one point as a possible singularity, then the category of perverse sheaves is equivalent, the category of diagrams like this, psi, phi, with two arrows, uv, such that 1 minus uv and 1 minus vu are invertible. They are monogerous. So here the corresponding concept is the concept of a spherical functor. We have two categories, say B and C. They're triangulated but with an enhancement. And as an enhancement, it can be either a DG enhancement or stable infinity enhancement. So triangulated enhancement. Either DG or stable. So we have a exact functor. We have the right adjoint functor. So if it's right adjoint, we have the unit and co-unit of the adjunction. F composed F star goes to the identity C, and identity B goes to F star composed with F star composed with F. And if we are in an enhancement setting, we can take the cone, which will be another functor. Equivalent. There should supposed to be equivalence. So we can say that this is, by definition, schobers, perverse schobers, categorified perverse sheaves on a disk with one singularity at 0. And we call such object S.
But here you do not have a condition that the one is adjoint to the other. So
Yeah, that's right. That's right. So that's right. So here I should have two of them. But in the categorical setting, everything sort of comes with a hidden scalar product, which is the whole. And this hidden scalar product also allows us to write this arrow and to categorify this condition. So when you see it for the first time, you see, wow, this is precisely one-to-one. So now let me continue a little more, some features of this. So I was talking about the graph, and now let me put a graph inside the disk. K would be called Kn, would be n plus 1 corolla. So it would be like for 1, this would be K0, but this would be K1. So this would be K2, and so on. So I said that for every graph there is some sheaf of cohomology with support. So if it's local, it will be the stock of this sheaf. There will be global cohomology of the disk with support in this graph. So I can write, so here H1 is support with K of df. Suppose this corresponds, to perverse sheaf F. So here it is simply phi, the space of vanishing cycles. Here it is psi plus phi. Here would be psi square plus phi, and so on. So for n thing would be psi, so not fully canonical, not canonical. No, so if it's local, yes. I mean, the fiber in the origin, yes. So, but I want to sort of look at this chain of spaces in the following way. So if I have just this arrow, some psi of phi, just one arrow u, then this is a group point. Like in theory of stacks, we have morphism of vector spaces, so this acts on this. That's the action group point. So in this simply the set of objects of this action group point. This is set of morphisms of this action group point. This and this, when they have object morphism, that would seems a pair of morphisms, would be nerve 2 of this thing. There's a set of pairs of composable morphisms. So let me just continue this part first and then okay, so I probably can move it a little. What? Okay. So let me say that. So let me continue here. So O psi to phi equals phi. Home.
Forgetting
phi
factor,
one
from,
and
forgetting
phi
factor for forbidden groups to sets. Yeah.
What?
I should say forgetting factor forbidden groups to sets.
Yes. No, I simply write down. So this is so is by definition set of psi for which it was u of psi equals phi 1 minus phi 2, something like this. Right? So, but it's home between phi 1 and phi 2. Now let's take all morphisms, which means disjoint union over all of this. So morph equals disjoint union over all phi 1, phi 2 whole. Phi 1, phi 2. And this would be psi plus psi cross phi. If you count, it would be this. Okay, so in general, so here we have nerve for Km, nerve M of this group point, psi. Now let me just say one more thing. So this thing has cyclic symmetry.
Should it be psi plus phi?
Psi plus phi, yes. This is simply my brain being fried already. Yes, psi plus phi. So the nerve of this thing, it will be psi times psi plus phi. So this has cyclic symmetry. So, and this is a simplicial object. Well, in this case, in vector spaces. But we want to accommodate for the cyclic symmetry. And we have the following proposition. So given psi to phi, the set of u, the choice of v such that psi phi uv is admissible in that sense. In one-to-one projection, extensions of a simplicial object structure on nerve psi phi to what's called paracyclic structure, which means that there is data tau n from nerve n to itself for every n, which would rotating the faces and degenerations, rotating the eye around the circle. and tau n to the n plus 1 is the monogram. So for some reason, just this also no one knows about the perverse shifts.
Sorry, so the monogram means the cone of one, 1 minus u.
Yes, 1 minus uv, so on the thing, yes. So this would be the center of the category, so this monodromy can use with everything. So now let me continue in this situation. So here we have the analog for Kn. We have a category called R Kn of this S of this schober, which is given by this data, is certain category which we call S n of f is the nth part of the relative Waldhausen category. Or Waldhausen space, as defined in algebraic case. So its features are very, very similar to what I wrote here. So it has a semi-orthogonal decomposition with n copies of B and 1 copy of C. So one can say that objects of this category are the following data. First of all, we have representation of the equivalent in B, and then f of Tn goes to C. So in particular, the very first one, S1, is this semi-orthogonal decomposition glued by using the function. And here we can have the analog of that proposition there. So let me make a picture of the semi-orthogonal decomposition. So this S1 effect. We have E, we have C inside, which is B orthogonal, then would be B double orthogonal, then would be triple orthogonal. We can iterate the orthogonals, and in this case, for this n equals 1, it's a theorem of Halper-Leinster. Shipman. That with f spherical. So f may be functor, may be spherical or not. If and only if the semi-orthogonal decomposition is 4 periodic. Which means that B fourth orthogonal would be B itself. So we go like this. So this is the second orthogonal, third orthogonal, and the fourth orthogonal will be it. This corresponds to the picture, corresponds to this picture here. So geometrically, in terms of categorical perverse sheaves, we have this category sitting here, and here we will have B, and here we will have B double orthogonal. And for this to be symmetric, it is.
Where is C sitting in this geometric picture? It's a fiber 0?
Well, no, fiber 0 is B plus C, so to say. So C is the orthogonal here.
Okay.
So this can be made, this can be made for any F. Any F, and this S dot of F is a simplicial category. So it's completely analogous to this nerve of the action group point. So more generally, what we prove F spherical, it implies that S dot of F becomes paracyclic. So it's completely analogous to this.
Should it be obvious to me that paracyclic implies for periodicity?
Yes, yes. In the situation, yes, yes, yes. Okay. What?
Oh, it's equivalence maybe, yeah.
Yes, it's equivalent. Well, if you say what does it mean to be paracyclic, yeah, it's equivalent. Let me do on this side now. The next quick part. Discuss. So this was on a disk. So intuitively, it's clear what to do on any surface. Let me do it. Schobers on a surface. More informal. And then later I say it in a more formal way. So we want to associate this to a surface.
Saying you should.
Oh,
Being paracyclic is some structure. You have to.
yes, we have to extend it. Yes, yes, and there are some assumptions.
Tau, you have to provide a bunch of.
Yes, the data assumptions.
Coherences and
Yes,
so on.
so paracyclic. Here we should imply the coherences. By the way, so
But
here when I
somehow,
say
if this is if and only if you're saying that all of
So-
the
so
issues,
it's-
space of choices is
there are some conditions to being paracyclic more than that I say. For instance, here, so I say it's simplicial category. However, in this simplicial category, there is more than there are phases and degenerations, and phases are adjoint to degeneration a certain way. So this was written in the paper of Dmitry Kaletin. So, for instance, so this is more, and here we have also to specify what is adjoint to what. So after that,
Oh, so some complicated two categories.
it's a complicated two categories. So what I'm about to write here, that show, yes, yes, yes. So this is should be completely formally, should be infinity two category. But let's not go there. So anyway, an object of this should be the following data. First of all, a local system of enhanced triangulated categories in the set before of triangulated categories on x minus m, and then a spherical functor near every point near every x in A in a compatible way, so that we identify the spherical shift of this spherical functor with the monodromy of the local system in a compatible.
In fact, I have to say that if you consider homogeneous surfaces, kind of not pieces of plane, one should go really to circle.
Yes,
bundle,
yes, yes, yes.
And it will be local
Yes.
system, not extend, but
Of
on
course.
this guy with monodromy 2 and all these things. Yeah, it's not
course.
it's
Of
not
course.
really shift
course.
on local.
Of course.
Yeah,
Yes, yes.
but it's
So here you had two categories, B and C. And so
нет.
how?
No, so informally, I'm saying that suppose I have a surface. Yes, so first of all, there is a yes. So suppose I have some points. So around this point, suppose I take out this disk. Then I can identify this disk with what I had before. So on this disk, I should. So this has to be in my notation B, and here I should put some category C and a spherical functor from B to C, so that the spherical reflection will be identified with the monodromy. And there is particular issue, like an issue of how is it Z graded or Z2 graded, that's what Maxim was saying. So let me first assume that it's Z1. So anyway, so if this is on this intuitive level, if K inside X is a graph, then we have a sheaf of categories. Those things give us I call R K of S on K. And if, again, X is with corners and K is spanning, X with corners, K is spanning, then we can take space of sections of the sheaf of category. I'll explain what it is. Gamma of K R K of S. So it is certain homotopy limit. It's a homotopy limit. Then it's independent, coherently independent on K. And it can be called the topological Fukaya category of X with coefficients and S.
And so local system means that we have a category with a strong action of the fundamental.
No, it's just with a weak action, of course. Everything is weak and
Weak.
well, yes.
It's infinity category.
Yes. So
Beginning, yeah.
you see, so here is the question of how politically correct do you want me to speak. If you have to speak completely politically correct, I can't say anything because it's very difficult. So strictly speaking, of course, this.
Say Lurie.
Huh? Yes, I can. Yes. Yes.
Then you can stop.
No, certainly it should be not actual action on categories, but sort of weak action.
Homotopy.
Homotopy action, yes, of course. So there is one thing which I wanted to mention, that this is gamma and not R gamma. Because when we say it, so this really means H0, H0. And in principle, there can be categorical higher homotopy. So, and this is separate direction which I don't discuss here. So it's confusing because we say if it's homotopy limit, that it's a derived function. But it isn't. It's analog of H0 in the world of categories. And analog of higher things would be something else. Okay, so now let me discuss the same thing in a more formal way.
The existence of this categorical HI is more related to the fact that I was decategorify.
Yes, for instance. Yes.
The
Yes.
K theory does not commute
Yes.
with global
So the real issue is how we think of triangulated categories. Do we think that triangulated category is an analog of a vector space, or do we think it's an analog of a complex of vector spaces? This has to be decided. If we think that it's an analog of a complex of vector spaces, then what we do, we introduce some triangulated structure on the kind of collection of triangulated categories. And where we get, by doing this, we get more or less in the theory of non-commutative motives, such as developed by Tabuada. And then we get nothing but K-theoretic invariance. But really what happens is that triangulated category is more like a single vector space. And in our paper with Alexei Bondel and Vadim Shechman, we did discuss an example of categorical cohomology of a schober coming from aberrational transformation. So with two things, H0 and H1. Let me discuss now this thing more formally. And again, let me sort of first discuss from perverse sheaf point of view. So description of f of xn. So again, it's for the surfaces as sheaves, so to say. So in general, it's a complex of sheaves. So if you take over any open sets, it would be a complex of vector spaces. It can have cohomology. But I want to stick to the pattern that we have a purity. And this leads to the concept which we call Milnor pairs. Oh, sorry. It's a pair of open sets on a surface. Let me make a picture, and that will be clearer. What? So the set U is going to be a disk. The set, let me write, U is a disk. U prime would be a disjoint union of disks inside U, but in such a way that they're sort of concentrated at the boundary. And U minus U prime is contractible, and so this U prime would be something like this. So in this part, and also I require that it contains at most one point in N. So in this state, intersected with N has cardinality at most one.
How can U minus U prime fail to be contracted?
What?
How can U minus U
So suppose U prime is in the middle.
Are you?
Yes, I assume like this.
So U prime is never allowed to be in the middle, always bounded.
Yes. Not all in the middle, yes. So what I have here, I have a thickened version of the graph. Of course, thickened version of that corolla which I have drawn. But since it's a thickened version, it can move around. So in this case, you have purity. In this case, we have hypercohomology in degrees other than 1 of U with respect to U prime of coefficient F equals 0. So we have only one vector space invariant. So each one is a vector space V. What? F is a perverse sheaf, yes. If a perverse sheaf, but on such pairs, it behaves as if it was a sheaf. With only one vector space, we can associate. It appears it's a complex, but this complex reduces to a vector space. So we can now, so let me call this F of U prime. Now we can formulate a theorem if you want, but the theorem is about perverse sheaves on the surface. Nevertheless, the category term of xn equivalent to the category of functors from the Milnor pairs opposite to vector spaces. So it is fine. So it's like sheaves, but on pairs. So first, homotopy invariance. Third is exactness. And exactness is this. Maybe I make a bigger picture here. So suppose I have many of those things. So basically I want to say that there are situations which would have not only pairs, but we have triples. So when we have a triple, normally we would have a long exact sequence of cohomology. But if the situation is such that in every degree there is only one, this is only in 1 degree, then it would be a short exact sequence. So exactness with means that if U prime, V are such that 3 pairs below three pairs would be, I have U prime, I have U prime united with V, and I have V U prime intersected with V. So if is this, then I write, I have 3 maps
It's U prime.
Hmm?
U prime.
U prime. Oh, yes. Yeah. Then it should be a short exact sequence. This exactness and the condition that if U prime is a single disk and U minus U prime does not meet N, then 0. So in this way, we sort of completely killed the perversity. It looks like a sheaf, except that we have this type of topology, not topology, it's not exactly a Grothendieck topology. The collection of such Milnor pairs. So then we say here, so let me first change this and then I continue. I see the finish. So a schober S on Xn is a datum, is again appropriate functor from infinity functor from up to either stable infinity categories, stable or DG cut satisfying similar axioms. So first homotopy invariance. So then exactness, so this short exact sequence will be replaced by a recalman of triangulated categories. So I write that S of U prime united V, I have S of U prime, I write S of V U prime intersecting with V. So that's what we have normally. Right? Let's call this map alpha, this map beta. In recalman we also have two adjoints. Let's call that alpha 1, alpha 2, this is beta 1. Beta 2, and moreover, those maps, alpha 1 and alpha functors, also come from the structure. So have a recalman. So in the same situation as there, we have recalman plus adjoints given by the structure, or come. So this means, let me explain what it means. So maybe I should write once more a good picture of such admissible triple. It would be something like this. So this was many parts of U prime. And if I put V to be something like this, that's an admissible triple. So, and in this case, we have several components, P1, same to PR, in this cyclic order. So I also write here normalization as before.
You still have this condition that there's only one point, at most one point?
Yes. Yes. So Milnor pairs is exactly the same condition. So in this case, we have this thing. We have U prime united with V. Now there is an inclusion in the poset of Milnor pairs, which is a homotopy equivalence of U. I can take this thing, and I can take, instead of this, I just take this thing. And that's an equivalence, if I ignore all of this. This would be, if I write correctly, U prime minus V united with P1. And this maps into U prime. So this, if I go with respect to my contravariant factor, I got sigma u prime, I go to sigma. This gives, because it's homotopy equivalence, with sigma u prime united with v, and this is going to be left adjoint. So basically, such a structure is a huge amount of semi-orthogonal decompositions.
Wait, just to understand what you said. So adjoints come from the structure.
So yes, it's a version of.
It's like stop removal statement, kind of saying that. These
Well, I don't really fully understand what you mean by stop removal, but I think it's similar. Yes. So this thing of adjoints is a geometric version of Dimitri's condition that faces are adjoint to degenerations in the Waldhausen in the Waldhausen construction. Huh? Oh, okay. I'm sorry. No, is it okay? Is it okay to tell them? Okay, to do it. Okay. I'm sorry. I hope I didn't say something. Oh, okay. All right. Okay. So. Yes. Okay, so now I am really out of time. I wanted to say something more. Or maybe I should just say one last thing. So last thing is called Lefschetz Schober. I really did, and Fukaya's idle cut. Suppose we have a proper holomorphic modes function. And this is scalar Calabi-Yau. And inside here we have set n, which is Wn, singular values. So this is basically what's called Lefschetz pencil. Yeah? So in this case, we have the standard picture of Lefschetz vibration that over a point Wi, we have the critical value is locus is singular, but there is a vanishing cycle, which is S. Suppose it's the dimension is on this one, SL. It's a vanishing cycle. So in this case, there is a perverse sheaf. There is a perverse sheaf which we take first take the direct image R W star of CY. There's a complex of sheaves on C. And then we take its nth perverse homology. This belongs to perv. I see. So in it so this perverse sheaf is on C minus n. It's local system of H n of W minus 1 of C. C and phi, the vanishing cycle at the point Wi, is isomorphic. C spanned and this nth sphere. So in this category finds to a schober, which we call the Lefschetz schober, LW, which it's clear how it goes. So outside is the local system of Fukaya categories of the fibers with respect to a Keller structure, and there is only one. The corresponding spherical functor is given by this spherical object in the Fukaya category of the fiber. And want to say so L double C minus M log 6 the Fukaya category. So near the I spherical function. So dV there with this category, which field K is sent to this object. It's a spherical function, and just to finish.
I have a question about this part. Is the endomorphisms of a spherical object supposed to be actually the cohomology of the sphere? Or is it allowed to, like, if I deform the cohomology of the sphere to be a direct sum of two fields, is that still a spherical object?
It would be a spherical object. So in what degrees? In degree 0, yes, it is a spherical object, yeah? It's a zero spherical object. You suppose it's K plus K.
Yeah, if I deform it to be K plus K.
Yes, I mean, in bottom degree 0, yeah, it will be a spherical object. Because zero spherical object, zero-dimensional sphere. It's okay. The zero-dimensional sphere is the most important, of course.
But if it's an odd-dimensional sphere and I deform it so that, like, the top class square is equal to 1?
That doesn't look good. No, I wouldn't say it. So finally, I want to say this. So now let's D inside C be a disk which contains all M, and we take it with one corner, attached. So consider it with one corner. So then the corresponding Fukaya category with coefficients of this D with LW is the Fukaya Seidel category of W. It's the category which has a semi-orthogonal decomposition, is exceptional collection corresponding to the vanishing cycles corresponding to the critical points. And the exact embedding of this exceptional collection will depend on the path, on the choice of the graph. So in this example of a spanning graph, so if you follow the procedure, we immediately grew the semi-orthogonal decomposition. But of course, we can consider Morse functions with values in other Riemann surfaces. We can have more corners. So we can have W, Y, X Riemann surface. We can have more corners, and so we'll be getting different. Okay, so I didn't have time to speak about the last part. To say about probably it's enough. Thank you so much.
Yeah. Do you understand this? Eventually, you just want to associate with simplification some two infinity two category for which and which you because all the semi-orthogonal decomposition are joint functions of Riemann.
Yes.
Examples of two categories.
Yes. What? Well, so here I'm getting sort of beyond my expertise. So it will be something that I think is called local Fukaya Seidel category. So once we can define it in a good way, it will work.
You just have to be a little bit more careful because a general lattice vibration won't have. That's why I asked about these odd things.
Yes.
The spheres could be obstructed.
Okay.
And
Yes.
also they could be odd in the sense that I said, where the top class square.
Okay. So yes.
The animals would be different. Yeah. So you have some.
Yes.
The definition of Schober in terms of a pre-sheaf on these Milnor disks, these Milnor pairs, it looks a bit like factorization algebras.
We were sort of playing with this. We were
Right.
getting excited with this, but then we didn't know what to say. Of course, we would love to say something like that. Yes.
Right.
Originally, we thought of some kind of round space. You see, the paracyclic category is something like the exit category of the run space of the circle. So again, but we couldn't say anything.
So you don't know what the analog of,
We don't know. Yes.
you like to say this is a co-sheaf on some run space, but you
Yes.
don't know what that run space is.
Yes.